Hello, ladies and gentlemen, and welcome to our webinar. Today, we will discuss the common challenge we end up when running distributed NoSQL databases at scale. We are going to have a nice chat over the considerations you need to be aware of when testing, deploying, and maintaining your workload at scale. Before we get started, let's quickly introduce ourselves. My name is Felipe, and I am a solution architect here at ScyllaDB. I live in Brazil, and I have a one-year-old puppy that I love more than anything. And it's very nice to finally meet you all. Along with me, I also have my fellow countryman, Guilherme, and he will be sharing with me, as well as presenting a demo that he prepared just for you people. So Gui, welcome. Thanks for being here. Do you mind introducing yourself, please?
Thanks, Felipe, and hey, everyone. My name is Guilherme, as Felipe mentioned, and I'm a solutions architect at ScyllaDB as well. As Felipe, I also live in Brazil, and I'm a technology enthusiast who likes to experiment with open source technologies and also open source gadgets. I'm also interested in gaming on Linux and database at scale. It's awesome to meet you all and have you here. So, Felipe, back to you.
And with that, let's get moving. So we are the team behind ScyllaDB, the database built for game changers. In 2020, ScyllaDB has been awarded InfoWorld's Technology of the Year. This is primarily due to the fact that the main proposition of ScyllaDB is to resolve the challenges commonly encountered with other NoSQL database solutions. For example, from a technical perspective, the primary reasons most of our users chose ScyllaDB is given the fact that it is able to, first, deliver high throughput. Second, provide lower latency response times when compared to its competitors. And third, all of that while reducing the total cost of ownership when compared to other solutions. ScyllaDB was created by Avi Kiviti and Orlaur, the founders of the KVM hypervisor, along with a multidisciplinary of system engineers and kernel hackers. As a result, we have a lot of experience on getting the most out of the underlying hardware, which explains how we have been able to achieve such consistent results. We are also an open source company. If you have never tried ScyllaDB before, just go to our website at www.scylladb.com and give it a try. In addition to that, we are also available in the cloud via our Scylla Cloud Database as a Service solution, as well as enterprise for on-premises and self-managed supported offerings. So one of the things that I like about this slide is that it clearly shows some of the many game changers that are currently leveraging ScyllaDB for their deployments. One of the things that, one of the reasons why I personally find this listing awesome is because it also demonstrates a variety of distinct use cases and industries who are currently powered by ScyllaDB. So just taking a quick look over here, we can see real-time streaming, real-time flight computation, social media platforms, blockchains, gaming, fraud detection. Whoa. So what's your use case and how can we help you? If you are still unsure whether ScyllaDB may be a good fit for you, please schedule a call with one of our representatives, and we'll be more than glad to assist you throughout your journey. Okay? All right, so let's get started. Today, Guilherme will show us a workload delivering close to 1 million operations per second with a single-digit millisecond latency, P99 latency response time of ScyllaDB. But before we get started, Gui, I have a question for you. 1 million operations per second, or 60 million operations per minute, or 3.6 billion operations per hour, or roughly 86 billion operations a day. What does that mean?
Sure, Felipe. 86 billion operations per day really seems like an impressive number. However, when you break it down by hour, by minute, and by second, it starts to become a reasonable range of operations. So for instance, 1 million operations per second might seem like a massive amount of operations, but for a distributed system, this whole workload will be processed by multiple workers, which in ScyllaDB case, they are called shards, which are the CPUs that compose your cluster. On a well-built system, it can deliver the 1 million operations per second operations as a target because every shard will be actually be performing a subset of the number of operations. So the cluster I'll demonstrate later today does exactly that. It is composed of 6 instances of i4R4X large, which has roughly 96 CPUs overall. In that setting, every CPU will be doing roughly 12,000 operations per second. Now, that doesn't sound like a lot, does it? That's the power of a distributed system, and in this case, the power of ScyllaDB, as it's built to linearly scale as you add more reserve processing power to your cluster, while taking full advantage of the hardware that it's deployed on. So, Felipe, does the 86 billion operations per day number look less scary now?
Uh, it's your explanation certainly makes sense. So, so let me see if I understood you correctly. The power of 6 instances that you are going to demonstrate to us combined are what makes the cluster capable of achieving such a high throughput, right? However, this essentially makes me wonder. We all know that hardware fails. You may end up with a network failure, end up with a split brain situation over your cluster. Essentially, things can go wrong when you're working with computers. So what are some of the considerations that you would recommend to our users when coming up with their cluster topology? And does it mean that the failure of a single node will be enough for ScyllaDB to be unable to achieve, according to your test, your promised 1 million operations per second?
Sure, that's a very good question. ScyllaDB is designed to be highly available and resilient to failures, both from hardware and software levels. The loss of a single node will not impact your cluster operation, nor it should impact its throughput. When setting up a cluster, you should plan for high availability by using multiple availability zones to compose that cluster, based always on your application factor. So if you're using the default replication factor of 3, then you should pick 3 availability zones. ScyllaDB's rack awareness automatically distributes data along the existing AZs to ensure the high availability in case of complete zone failure. The cluster continues to operate normally even under a catastrophic situation. The recommendation of going with a replication factor of 3 and also the choice of the consistency level can make or break the availability of a cluster in case of an outage. We always recommend your replication factor of 3 and consistency level of quorum. So if the case of complete zone failure, your queries can still complete in a consistent manner. And when the service is restored, the data can then be replicated successfully to the joining nodes to restore your service completely. Applying the best practices, such as the zone deployment choice, they're crucial for the functionality of the cluster under the extreme situations. So make sure that you follow Scylla's great documentation on choices when setting up a cluster for reaching maximum availability and resiliency. And in general, you should follow the best practices throughout your testing that ensure you maximize your chances, Felipe.
Thanks. Yeah, one of the things you mentioned about our documentation, that's typically a very good feedback that we receive from our customers. Our documentation is typically very extensive and very detailed. So thank you very much for that. Another thing that I'd like to tell you, in case you're not aware, is that you have a very beautiful voice. So I am quite enjoying listening to you talking. But let me go ask you from a different perspective. So far, we have only talked about technicalities. From a business perspective now, and also from your own experience working with a variety of customers and use cases, I think that 1 million operations per second, that's definitely an impressive number. Which kinds of use case need such high throughput? So certainly one of the use cases that first come to my mind are real-time ones, such as, for example, think about Twitter, right? Where multiple users are interacting with each other, liking tweets, all concurrently, and everything is happening, everything is communicating with the database at real time. Do you have any idea about any other types of use case who may benefit at such scale?
Absolutely. Many use cases require that level of throughput. A busy ad bidding service or IoT collection and analytics platform, a real-time chat, as you mentioned, or social media. Today's industries have the need to go beyond what traditional databases can offer, especially when in cases where it's more than a single server can deliver. So that's why computing at scale can only be achieved by a distributed database, especially ones that are focused on providing the high throughput, low latency at scale, such as ScyllaDB. Industry leaders are seeking ways of expanding and deepening the analysis of existing data, enriching decision making for analytics insight, for instance. Then it's easy to understand why use cases can easily reach or even surpass the million of operations per second level. Think of a streaming service use case of watch history. It can be used for different purposes to display the last watch programs that allow users to resume where they stopped, that also to display the list of titles that are still in progress so the user can just resume them, and also to enrich the user experience by using all of the data to recommend relevant titles so the user keeps engaged on the platform. The streaming service has dozens of millions of, if the streaming service has dozens of millions of customers, then it's easy to see how that use case can surpass the million of operations per second mark. And it maybe even need more as it scales in the future. So I'm sure you've seen multiple use cases such as this big one, right, Felipe?
I definitely have. I definitely have. Yes. So good, 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 good. All right, let's move on. So now that we understood what 1 million operations per second represents, and now that we understood that your demo is essentially not going to run us bankrupt, since you, as at least you're claiming you're going to be running it on top of 6 nodes only. I want you to see that because 1 million operations per second on top of 6 nodes is definitely impressive. But let's talk a bit about the infrastructure now that you're going to show us. So at the beginning of our presentation, I have mentioned that one of ScyllaDB's goals is to provide our users with a very aggressive TCO reduction towards their infrastructure expenditure. So given the fact that you are going to demonstrate your demo running on top of only 6 nodes, and that you are promising us to do so under a single-digit milliseconds P99 latency, can you please elaborate more on the infrastructure, the stress tests, the tooling, and the specific conditions that you will be covering in your demo?
Sure. For this demo, I used, as previously mentioned, a 6-node cluster of I4 4x largest. And to stress it, I also used 3 nodes of R6A 16x largest. That will be running Cassandra Stress with a custom design user workload. The worker nodes have a CPU ratio of 1.75 to 1 towards the Scylla cluster. This is intentional, so as we use the multiplication factor of 3 and consistent level quorum, as a system configuration, we need as many CPU on the worker to stress a Scylla cluster. The cluster setup is enough to deliver single-digit latency P99s for reads and for writes, while doing 1 million operations per second. The workload reads most of the data from cache, that's including the recently updated data. So the latency is reflective of that workload that relies heavily on cache data. Does that sound reasonable, Felipe?
It certainly does. It certainly does, especially the fact that so in order for you to have achieved 1 million operations per second, that's certainly a workload that requires to be reading fairly frequently from cache. That's interesting. So before I actually ask you the next question, let me turn back to our audience and say, remind them that if you have any questions, feel free to drop them into the chat. Okay. Okay, great. So one of the important aspects that I think it's worth mentioning fact that not all use cases are the same. So not all requirements are the same, and definitely not all the technical aspects which differentiate one use case from another are the same. For example, a specific use case may read more from disk than from memory, which would be essentially the opposite of what you're going to show, will be showing us today. And another use case may have a larger payload size or different access patterns than the conditions exhibited in your demo. As a solution architect, you and I frequently work with a huge set of distinct requirements. Can you please elaborate a bit on what are some of the aspects that one needs to consider when trying to achieve their own 1 million operations per second?
Sure, Felipe. So as you mentioned, the payload certainly makes a ton of difference with regards to the throughput expectations of a cluster. After all, a payload of 1 kilobyte while at the 1 million operations per second mark means roughly 1 gigabyte per second in throughput. If the payload were larger, let's say 100 kilobytes, then the expectations of 1 million operations per second might need a different hardware setup. Calculating the expected throughput using the operations per second and the payload size is extremely important to design a system that can deliver the high throughput and still keep latencies in the single digits. The ratio of reads and writes is also very important, as both have different weights in Scylla cluster. Ingesting data is extremely cheap for Scylla, and reading data is still very performant. Using materialized view and indexes add overhead to every write, so it's also important to consider them while you're planning a system. So as I previously mentioned, the usage of a cache is crucial to low latency. So it's important to ask, how does the application read the data? Is historical data being constantly read, or is it reading recently inserted fresh data? Are analytics process polluting the cache? Keeping in mind that analytics applications should always be designed in a way that avoids impacting the live user workload, which can be seeing different aspects in the cluster. Like live user workload cache should not be disturbed by a long-running, heavy analytics workload. CLDB's enterprise feature workload prioritization, as well as the CQL extension bypass cache, can help users running this scenario. So I hope this cleared things up, Felipe.
It certainly does. And on top of that, about there are certainly many aspects that one needs to consider when trying to operate a distributed database at scale, specifically with regards to a payload size. Depending on your payload size, one of the things that you need to remember is that it may be simply too unrealistic for you to achieve a certain latency. So for example, size of, I don't know, 1 megabyte, it's not that uncommon. You cannot expect to always have a single digit millisecond latency with that payload size, because eventually you're going to hit a wall, a physical wall, which is essentially going to be your network, especially as you try to run more and more operations per second. Okay, thanks, Guy. And let's move on. So how do you get started, Guy? I mean, if I had never worked with ScyllaDB before, but I already have some experience with, I don't know, either DynamoDB, Cassandra, or any other NoSQL database, what do I need to know before I start adventuring myself? We already know that we need a distributed ScyllaDB cluster, because you mentioned that you were going to run a 6-node cluster. We also need either an application or a benchmarking tooling, right? Which in your case is going to be Cassandra simulate or production workload. What are some of the considerations needed when I'm getting started? Some of the common mistakes that you've learned from our experience, and most importantly, is there any observability tooling which one can use to gather results through their journey?
Sure, Felipe. So in order to get started, you need a cluster running on good hardware. If you're doing anything performance related, don't expect a Docker cluster running on your own laptop, as best as your laptop can be, to perform well. So Scylla needs the best hardware you can get, the fastest and most numerous CPUs, and also lots of memory and fast disks. Our recommendation for cloud instances is to look for locally attached NVMe drives, such as the i4R family on AWS, which I'm using for this test, the N2 HiMem on GCP, which allows you to choose locally attached disks, and also the X-Standard LSV2 on Azure. Of course, I picked i4X larges because they have Nitro SSDs and very fast CPUs, along with lots of memory. So this is what a high throughput, low latency database needs. Also, it helps that the database is able to squeeze every ounce of performance out of the hardware. As a benchmarking tool, the go-to solution for SQL is Cassandra Stress, which is designed to replicate workloads using the SQL protocol and can be used to stress a Scala cluster. Cassandra Stress allows you to design custom workloads using the YAML file, and it's great for complex scenarios and using multiple parallel queries. When you're using it to stress Scala, make sure that you use the Cassandra Stress binaries that are provided by the Scala Tools package, as that package contains our Scala-specific shardware driver that's for the best performance of your testing. The YCSB2 can also be great to stress multiple databases, including Scala via the SQL protocol, as well as Scala's alternator, which is DynamoDB compatible API. Also, make sure that you pick a good server to use as your stressor. Scala's top-notch design can hardly be defeated by a stress program written in Java and running a tiny instance. Stressing with no monitoring also make no sense. So you should always definitely use the Scala monitoring stack to collect and analyze data throughout your whole testing. This freely available stack can grant you insight on database internals and expose tons of metrics that you ease the understanding of how the database performs under your very different tests. So the bottom line is never ever benchmark without monitoring, right, Felipe?
Never ever benchmark without monitoring. Please, yes, that's a very common mistake we see. People often doing what you said about running on top of Docker. Trying to do performance tests on top of Docker is simply a no-go. We have many articles. You should not be doing that. But yeah, I mean, I think in general, if you don't want to go through the hassle of setting up your own cluster, configuring or managing it, remember what I said in the beginning. ScyllaDB is also available as a database as a service offering. So this is essentially the landing page that you're going to be greeted up on if you eventually sign up for Scala Cloud. It takes like 2 minutes, and then you're going to receive an email, confirm your email, etc. So essentially, let me give you a quick walkthrough on how it works. You're going to land on this page, then you can click New Cluster. You're going to be providing your cluster the name, so let's call it Webinar. And then you can choose whether your cluster will be running AWS or in GCP. Those are essentially the locations where Scala Cloud is currently available. One important aspect about ScyllaDB, in case you are not aware, is that we essentially are compatible with both the Cassandra API and also the AWS DynamoDB API. So if you are coming from Cassandra, or if you have more familiarity with the Cassandra API, the SQL protocol, choose this one. Otherwise, if you prefer DynamoDB API, you can choose the DynamoDB. As after, essentially, what you're going to do is to select the instance type that you want. And in the case for this demo, Guilherme is going to be demonstrating as a 6-node cluster of i4i for X large. Okay. And then what you have to do into network settings. If you want to eventually do VPC peering to your cluster, either via your AWS account, or if you are provisioning from GCP, from your GCP account, you can select this button over here, and then you can select which network your cluster is going to run at. I would just stick with the defaults, but in case you are wondering, you don't have to use big network block as it's currently here. You can choose a smaller one, so don't worry. And then essentially you go and click launch cluster. And now essentially I'm burning ScyllaDB's money. So after some minutes, the cluster will be up and ready, and then you'll be able to connect and start playing, doing your actual performance testing. One of the things that I would like to mention is, in case you don't like to go and clicking around, in case you are an automation freak, ScyllaDB is also compliant with your favorite infrastructure as a code tooling. So for example, we have a Terraform provider, which allows you to easily manage your cluster resource as you are already used to, if you are working frequently with cloud vendors. Okay. Okay, so now that you have seen how easy it is for you to get started, let's switch over to our actual demo. Guy, the audience is yours. Please break a leg and make me proud.
Certainly. Let's start sharing my screen here. So, oops, before I show you the actual monitoring data, I want to show you the test that I'm running. So this is my custom demo template that I use for a custom template for Cassandra Stress, where I define a key space that's called key space value test. I use network topology and replication factor of 3, and also create a table called key value example, where I have a key and a value, and a column specifications for keys and values. So I basically create a 1 billion entries on cache, and this is used to be populating the database before you actually doing the test. Then I creating additional statements for running inserts and creating queries that will select entries from my distribution. Now let me show you how my monitoring is. So I pause refresh because otherwise it's just blinking lights. Here we see that this is Scylla's monitoring, also monitoring stack, demonstrating how the cluster is performing under 1 million operations per second. So as I mentioned, this is an 6-node I4R 4x large cluster, which is a tiny number of resources if you think about it, performing 1 million operations per second, which is a 1 kilobyte payload, as I demonstrated before, doing an average write and P99 write under a millisecond, and also an average read and P99 read also under a millisecond. Keep in mind that, as we discussed before, this is reading data from cache, or mainly from memory. So this is why we get extremely stable latencies. What we see here is that for writes on the writes panel, it's reporting 333,000 writes operations. So our write is 1/3 writes and 2/3 reads. And in regards to reads, it's 7,000 operations per second. So there you go. What 2/3 are reads out of 1 million. Write latencies are stable under 2 milliseconds. You see that the P99 spiked over 2.3 milliseconds, while read latencies are very stable at 600 microseconds. We also have Scylla's amazing advisor dashboard, where it shows us some details on the workload that is running. I purposely created some imbalance on the test, so we have some shards and SS tables that are larger than others. This should not impact the test, but I wanted to create something that shows you the power of the advisor board. So here we have balancing alerts regarding connection, CQL operations, node and shard latency for cache utilization, and for the number of SS tables. In this case, I have a shard that is creating more data, more updates to data that will be flushed to more SS tables on disk. That will trigger the alert that's showing that there's some shards that reads more from SS tables, and that node could be slow. So this is just an imbalance to show how it can be, it can be used to catch some errors, some failures of design of the application level from the database side. Also, we have information per DC, which I have a single data center. We do show what is the load utilization overall, which is 93% CPU utilization, the disk utilization during my whole testing, how many compactions are running in that specific DC, what is the cache hits and misses ratio for that data center, historical and current write payloads, and also read operations, also historical write latency and read latency. We also have a nice panel that shows all the nodes in the cluster, their current version, what is their status, how many nodes it sees live in the other end, and what is the load utilization or CPU utilization for that specific node. We do have more menus here, so I'll show you now the detailed menu. When you're looking into detailed panels, you basically have the option of filtering, which is really nice when you have to understand how is your cluster doing. But you can also you're also able to drill down into very specific details. So automatically, all filters are by DC, but you can also filter them by cluster, which as I have a single DC, it's basically the same view as by DC. And then I have the option to filter by instance. So the by instance show me all the 6 instances and how they're performing throughout my test. So I do have the option of looking to how they were performing, receiving queries, what are their latencies, and every kind of metric that I do have for monitoring, also from the instance level. And also I can dig further into the shard level, which is each CPU in the shard, in the cluster. When I look it through the shard level, we see that there are much more entries here. So it's basically 16 CPUs per node. But we do have all that same information per shard. So if I zoom in into requests served per instance shard as a coordinator, which means that those shards are being targeted by my source application as a destination for my requests. You see that it's balanced, but it still have some shards that are reporting a little more reads per second than some others. This is the imbalance I purposefully created. Felipe, do you have a comment?
No, yes, I do. And I also want to follow up on one of the questions we received in the chat.
Sure.
So the question is essentially, let me see if I haven't lost it. I think I lost it, but I'm going to find it. Yeah. What about additional metrics which are of more help compared to Cassandra? I know that you're giving us a deep dive into monitoring, and eventually you're going to a dashboard which Cassandra has nothing similar. But now that you're talking about shards, what does it mean? What's a shard in Scala, and how does it differentiate from Cassandra? Can you explain that to us?
Sure. So Cassandra shards by node level, also from vCPU level, which not vCPU, but vNode, but that's the maximum that Cassandra sharding can do. Scala also shards on top of node and vNode, also by shard. So every CPU in your cluster will be a unit of work that you own a piece of the token range, and all the data and requests that are put towards that piece of data. So every unit of your cluster is actually a separate unit. So every shard is only responsible for a subset of the data. And if you nail your design, your schema, and your queries, you're basically distributing the workload throughout the cluster and putting the whole cluster to work for you. That's opposed to having a hot partition where multiple users are using it instead of distributing the workload throughout the system. As opposed to Cassandra, which will shard you by node, so it's harder to see that imbalance. Here, as we shard by CPU, we easily can see some data skew, even though it's still in the 10% range. It still makes a difference and allow us, and the monitoring empowers us to dig further into it and know exactly which nodes and shards are involved, so we can track it down, uh, run tracing, run node to top partitions, and basically diagnose an access pattern without having to resort to very heavy probabilistic tracing and everything of the sort that will be overkill for just getting to understand this point. Okay. So I'll keep showing my metrics on the shard level. So we see that Scylla reports every metric by all the respective levels. So you can see them by cluster and DC and also by instance and shard. So when you're diagnosing issues, you certainly need to look into how the cluster is doing. So okay, is my cluster performing well? But some part of the cluster may not be performing that well. So when you need to diagnose that kind of issue, you look into the instance level to see if one of the instances may be popping up with regard to the others, and within that instance, the shards that are being reported. So you may see that a single shard on your whole cluster may be misbehaving, maybe a customer query is hitting that shard over and over, then you may have data imbalance or a data modeling issue, and monitoring will certainly grant you a lot of visibility and instant access to how that shard is performing. So we do have metrics about foreground writes and background writes, which are when writes are being accepted or being put to wait from the from the client perspective, and also foreground reads and background reads, which is when Scylla is working on requests that are being received by clients from client perspective and also for internal database perspective. Speculative data reads, which is when Scylla's internal data manipulation engine requests for additional data from other nodes in order to fulfill its queries. We also have metrics such as timeouts and errors for the coordinator reported by shard. Here we have no timeouts, but we're basically, if you're seeing timeouts, you can drill down into the very detailed level for where is that being generated. What I also want to show you is how the reads with misses and cache is being reported. So here we see that reads with no misses is basically reporting around 8.1 thousand operations per second per shard. So each shard is delivering 8.1 thousand requests per second from memory, while reads with misses, which is when Scylla has to reach the disk in order to retrieve data, is reported as 0, because as I previously mentioned, this workload is reporting data that is being read from cache.
Yeah,
Felipe, do you want to comment?
yeah, I mean, that's impressive. I mean, over 8,000 operations per second in a single CPU. That's that's a very efficient usage of CPU cycles, if I'm allowed to say. But I think that in general, one of the things that I'd like to mention here is that's all of this is possible. I mean, it's not magic. It's not like we are wizards or anything. I wish we were, though. Scylla essentially has this shared nothing architecture. Gil, would you like to explain a little bit about what does that mean?
Absolutely.
Or
So
shared nothing architecture?
shared nothing basically means that every resource in Scylla is dedicated to shards. So every shard has direct access to its own subset of memory, and also for I/O and networking. So there are no locking between shards. So as you would say, locking between threads on Cassandra, which is when threads are basically competing for the same resource, either it being memory, I/O, networking. So in Scylla's shared nothing architecture, every shard has full direct access to its subset of memory and can easily access it for writing and for reading. The shared nothing architecture is built on Scylla from the ground up. So every aspect of a shard is basically independent from each other. I'll keep showing you because time is running, so I'll just drive you through how also Scylla's LSA total memory, which is basically data that is being stored from queries, is being reported. You see that all shards are basically having 7.6, around 7.6 gigabytes of memory per each one of them, and also additional memory in order to control or metadata from internal Scylla's working. We also do have running compactions and compaction CPU time per shard. So we see that every compaction job that is started towards single shards are reported uniquely, and you can track those down as well, as long as the CPU time that has been consuming from processing. Here, the greatest view is to view latencies by shard. So we also see the request that each shard is being performing, and also the average 95 percentile and 99th percentile for reads and writes. So you can even drill down to latencies at the shard level to understand how your cluster is doing and how's the cluster health. So I'll also show you other panel, which is advanced. I also filter by shard to make it more sense. We do have information on commit log, so how commit log, which is the data persistent from write requests, is being stored on disk, how much bandwidth is it consuming, how many operations per second, what are the shards that are most consuming, and what is the queue delay for each of the shards. The same goes for compaction, for default class, which is all queries that internal main table flushes, which is when data from main tables are flushed onto disk, creating SS tables. For query, which is general queries, and SL default, which is the service level default main class of queries, which is the one I'm using for my tests. Last but not least, also streaming. So when you stream data between nodes, you see that exactly how is that performing, how much bandwidth and I/O that's using the background. There's also the information by task group, which is the same groups that exist before, but reported by CPU utilization or CPU time. Also time spent by quota violation, which is when tasks take longer than expected from Scylla's perspective. And what is the scheduler shares, or how is the priority of that task as compared to the other ones. So you have that kind of metric for uh, filter exits, background reclaims, compaction, gossip, which is internal gossiping protocol to keep all nodes in sync to the metadata and cluster topology level, main class, memory compaction, mem tables, mem table to cache. Also, last but not least, service level default, which is the service level I'm using for my queries. We see here that around 77, 78% utilization of CPU time goes straight for my queries, and also the time that is used by shard for streaming, which is when one instance is streaming data to our daughters. The last dashboard I want to show you, which is I think is the most relevant one, is Scylla SQL. So Scylla SQL, which I also need to filter by shard, shows you every operation that is being sent towards coordinators. So every insert, read, delete, and update is being reported directly here. So you can see there immediately how is your cluster receiving your requests, what kind of requests those are. Also, it reports the client SQL connection by shard. So when you're using a shard-aware driver, which in this case I am, it basically shows you how many SQL connections each shard is holding active throughout its lifetime. We see here that one shard has 4 connections reported, while some of the rest of them shows 3. This is because I'm using 3 nodes to stress my cluster, and each one of them is running one Cassandra stress process, while the 3 basically means that every Cassandra stress process is open a single connection towards every shard in your cluster. So it's basically opening a communication channel to every CPU in my cluster and keeping on one additional connection for metadata and just for keeping the communication with the cluster alive. We also report how many SQL row has been read. So how many rows it being returned to the client. Sometimes you can do a query that has many pages that would slow down the database, and you can clearly see when those queries are being ran and what are the number of pages and which shard those are affecting. There are a ton of more information here, but it's also important to remind that we're only able to reach this 1 million operations per second mark in such low hardware, if you think about it, because we're following all possible optimizations that you can do in a Scylla cluster, all best practices. And that's why the Scylla optimization dashboard shows you. We do have a lot of recommendations that is being capturing data from your live workload and recommending to you how to fix and analyze those issues. So you have alerts as regards to SQL non-prepared statement, which is when you're not preparing your queries or not preparing them correctly from your application side in order to reuse them more efficiently. If you're doing non-page SQL reads, which, as I mentioned, if you're asking for a lot of pages that will basically put pressure on the database, you should always page your queries. And you will see those queries being reported, those reads being reported here. If you're using non-token aware queries, if you're using reverse SQL reads, allow filtering SQL reads. If you're filtering too much when you're using allow filtering, because allow filtering is one thing, but if you allow filtering and removing 99% of your data, then you should look into a better and most effective way of doing that query. And all of that you can infer from the information that is gathered in these panels. Also, range scans without bypass cache, which is when you're basically bringing a lot of data into memory. Also, kind of like doing a analytics workload without using bypass cache, which is when you're polluting your memory or in your cache for your live user workload. If you're doing SQL consistency level any or consistency level all, which will bring you inconsistent result and a lot of pressure on the database, depending on the use case you're facing. And also, last but not least, if you're using cross-DC queries, that will make your latency spike because you're basically incurring geographic latency spikes in your queries. And you basically need to understand that if you're doing that, you pay the price in latency. And the recommendation is, of course, that to keep latencies local to your data centers. So I think that that's it. I'd just like to show you, demonstrate to you how such a tiny Scala cluster can effectively extract as much as it can from hardware and to deliver a 1 million operations per second mark at 1 kilobyte payload range while still performing extremely nice workloads. Sure, Felipe.
Do me a favor, click on the requests and make it explain the requests.
Your voice. Oh, the requests. Okay.
Yeah.
Let me go back to. You want to see that by DC?
No, go back to the overview.
Oh, sorry.
Yeah, requests, see 1 million.
Oh,
Click
sure.
on it. Yeah.
Sorry.
Yeah, that's what I wanted to see.
Yeah, that's it.
Awesome, guys. Awesome. Sorry. I had to do this. So we are almost done, guys. Thank you, Guy. Let's take a quick poll so we can to know your use case better. How much data do you have under management of your transactional database? I'm not sure if the poll is going to show up, but we'll give you some time to answer now. Where's the poll? There. And I see a lot of people are answering. Thank you very much. Thank you very much. All right, so let's give it some more seconds. Wow, a lot of answers. Over 100 terabytes, over 10 terabytes, over 1 terabyte. All right. Thanks, everyone. Thank you very much for answering. And this essentially brings us to our Q&A panel. Before we dive through all the many questions that I see in the chat and in the Q&A, we have added some amazing content for you to learn more about ScyllaDB. So Scylla University is a free learning platform within ScyllaDB that goes from the very basics up to more advanced content. It is our de facto recommended learning resource for you to get up to speed fairly quickly. So if you have never learned about ScyllaDB and you'd like to get started, go to ScyllaDB University. In addition to it, we have also recently hosted our ScyllaDB Summit event, which included talks not only done by ScyllaDB employees, but also several customers explaining how they leverage ScyllaDB across their environments. I encourage you to watch our ScyllaDB Summit on-demand content And I'd like to personally highlight the talks from Discord over their challenging migration of a production cluster. Optimizely, who gave us a technical deep dive on how to benchmark distributed systems. And Epic Games, who basically detailed very nicely their overall usage of ScyllaDB for their Unreal Engine platform. Now, I can see that we have a ton of questions popping up. Guy, do you mind taking the first one, please?
Sure, sure. One of the questions, I'll share this. Yes. From how does Scylla scale with the number of tables? So for example, how does the performance of a cluster with 20 tables compare to one with 200? So the point here is not exactly about the tables itself, but the different use cases that you're putting the cluster towards. So with 200 tables, you're basically mixing too much data to make your cache effective, to make your balancing effective. And that's just harder for you to manage whether queries are interfering with each other. Of course, that it still performs extremely well and way better than Cassandra. But I think that's besides the point of just having the table, right? If you're just using the table and keeping it up for a later use or analytics use case, I think that makes sense. But if you're expecting low latency, high throughput for 200 tables, 200 different tables with interweaving use cases, interweaving read and write patterns, that may be not be the best answer for you. So if you're striving to focusing on higher throughput and lower latency, I think the best option for you is try to isolate the use case that need it and the use case that don't. And the use case that don't need that strict latency, then it might be a good option for you to mix those, because polluting the cache with different use cases will hurt your latency, but at the same time, you're okay with it, right?
Thanks, Guy. Let me
Sure.
take two questions because one is very simple and the other one is one I would like to elaborate a bit more. So
Nice.
Fernando asked whether this session is going to be available to be watched on demand. Yes, we are going to be sending you an email. And Anderson asked what would be the best approach to identify a hot partition? That's a very good question. So first, what's a hot partition? Key in your data modeling that frequently gets accessed. So you are either writing too much to that key or you are reading too much from that key. If you paid attention to Guilherme's monitoring presentation, the very first thing that you will do in order to identify a hot partition is once you switch to the per shard view, you are going to see that the very same shard across 3 replicas, if you have a replication factor of 3, you will notice that those shards will essentially be standing out from the others. So that's the first sign that you may have a large partition. Yeah, is essentially that. After that, how do you know what is the partition that is essentially getting hot? There are multiple ways for you to actually figure it out. One way is for you to simply run a command called node to top partitions, and this will essentially scan how many queries you run for a given period of time, and then you will be greeted back with essentially a listing of all the partitions that were hit and how many partitions and how many times those partitions were hit during your sampling period. If you have a use case that is prone to hot partitions, one thing that you maybe want to look at is a new feature that ScyllaDB has that Cassandra doesn't have. I'm only mentioning this because I see many people asking questions. How does ScyllaDB compares with Cassandra? What's best in ScyllaDB than Cassandra? So that's why I'm mentioning Cassandra. So recently, we made available a feature in ScyllaDB called per partition rate limiting. Okay, so essentially, it's a setting that you are going to configure in the table level, and then for every partition that exists in your table, you are only going to allow a specific amount of requests per second. And that's essentially how this feature works, per partition rate limiting. Okay, so I hope I answered your question.
Good. So I'll mark this question as answered. Do have a ton of questions. Guys, we're not able to reply to every one of you. So if you still have pending questions after the webinar and you still want to pursue answers for those, you can email me and Felipe and we can surely follow up with you later on.
Definitely. So thank you very much for all those questions. We are going to follow up on all those questions. So don't worry. Eventually, you're going to hear back from us. So guys, well, we are unfortunately almost running out of time, and we want to be respectful to all of you. So thank you all for today. In due time, you will find this presentation available on the siladb.com homepage in our webinar section for on-demand viewing. I hope you enjoyed this webinar. Gui, bro, any last words from you?
Thank you everyone for joining us today. It's been a pleasure to have you here, and thank you for the interest in ScyllaDB.
Thanks everyone, and see you soon.
Bye-bye.